like it is time to begin, so we will go ahead and get started. A couple reminders you can see on the screen there. If you are enrolled in Chem 141, the density of metals lab is open, and you should do that at your convenience this week because it's due Sunday evening, and also I'm going to be posting a new lab for you to do later in the week, and you don't want to get too far behind on that. And then also, I know that most of you have, but if you have not yet paid for the Chem 101 app, your free ride ends on June 15th, so you can just go to the website and pay that before then. Okay. All right. So we're going to go over today. This is a very dense lesson, just to kind of get you in the right mindset. A lot of very important chemistry, real meat and potatoes chemistry kind of stuff we're going to go over today. Starting with percent composition, and then we're going to lead into stoichiometry, and then the whole concept of a limiting reactant. Okay, and that's what your pre-class activity had to do with, was the limiting reactant topic. All right, so let's start with percent composition. So anytime you have a compound, you can say that that compound is a certain percentage of each element that is present in the compound. And the formula for deriving that percentage would be something like this. So the mass percent would just be equal to just the average atomic mass of the element that's present, and you divide that by the formula mass of the compound as a whole, and then multiply by 100%. And so, for example, if I want to calculate the percent potassium and the percent chlorine in this compound, potassium chloride, then I would do it like this. Okay, so first of all, I'm going to need my periodic table, because I need to determine the mass of calcium chloride. And so potassium chloride. So if you look up potassium, you see that its average atomic mass is 39.098. Okay, and you're going to add to that the average atomic mass of the chlorine, which is 35.453. Okay, and that's going to equal some number. All right, and so then if I want to figure out the percent of potassium in potassium chloride, that's going to be equal to, well, you know what, I'm going to go ahead and do that calculation just so I can have more numbers to work with here. So I add 39, I'm doing this in my calculator, 39.098 plus 35.453, and I get 74.551. So that's 74.551. And remember, that's units of atomic mass units. Okay, so to calculate the percent potassium, then I would take the value for potassium. This is for potassium, and this is for the chlorine. So I would take the 39.098, and I would divide that by the total mass of the compound, which is 74.551. Okay, and I just multiply that times 100%. Okay, and I'll let PowerPoint do that for us in a second. And I do the same thing for the chlorine in this compound. Okay, so that would be the 35.453. You divide that by the mass of the compound as a whole, 74.551, and you multiply that times 100%. And so that gives you the percentage of chlorine in this particular compound. Okay, so I'm going to erase all that. Oops, I don't know what I just did. Okay, so display that. So the average atomic mass, or the average formula mass for potassium chloride is 74.55. So the percent potassium would just be the average atomic mass of potassium from the periodic table divided by that number of the compound as a whole times 100%, which comes out to be 52.45% potassium. I can do the same thing for the chlorine. So this is the average atomic mass from the periodic table for chlorine divided by the formula mass for this, this compound times 100%. And that comes out to be 47.55. Now, one thing to notice is that if you add those two numbers together, that equals 100%, because obviously you have to, have 100%. If you added all the percent masses together, they should add up to 100%. Okay? All right, so that is how you could figure out the mass percent of each element in a compound. Okay, so let me do another example for you, and then I'll probably get you guys to do one of these. So we want to figure out the percent hydrogen in methane. So first of all, what I need to do is figure out the molar mass of methane. Well, that's going to be 12.011 for the carbon, plus 4 times 1.008 for the hydrogen. Okay, so that's going to be 12.011 plus 4 times 1.008 equals 16.043. Okay, oops, atomic mass units. And so in this case, if I want to do the percent hydrogen, one thing I have to do is since there's 4 hydrogens in the formula, I do use the average atomic mass of hydrogen from the periodic table, but I also have to multiply that times 4 because there's 4 hydrogens. And so, you know, there's 4 times that amount of mass in this compound due to the hydrogen. And I still just divide that by the molar mass, pardon me, the average mass of the formula as a whole. That should be a 4. Okay, times 100%. Okay, so I'll let PowerPoint take over for that. Okay, so 16.04 for the whole formula. And then the hydrogen, just, you know, recognize that you have to multiply it times 4 because there's 4 hydrogens in that particular compound. Okay.
Wow.
And you get 25.14% hydrogen in this compound. Okay. And so if you want to know what the percent carbon is, then that's pretty easy because there's just 2 elements in this compound. There's carbon and there's hydrogen. I know that it's 25.14% hydrogen, so that must mean that the rest of it is due to the carbon. So that's what this bullet is all about. If I didn't want to do this kind of calculation with the carbon, you could, but if you want to kind of cut to the chase, then you can just subtract the 25.14 from 100 to get the 74.86% carbon, because all the percentages must add up to 100. Okay? All right, so now I think I'd like for you guys to try one of these. So let me get you started on a Chem 101 activity. So this will be 2A. So you should, oops. Okay, so you should be able to start that now. Okay, looks really good. So I'm gonna go ahead and move on. All right, so now that was kind of a background for us to talk about this other thing called the empirical formula that we can derive from those percent compositions. So this is kind of going in the other direction. So let's say that we know the percent composition by element of a compound. From those percentages, we can actually come up with the chemical formula, you know, like the elemental symbol and the subscripts. That's where we're headed. Based on these percentages, we're going to derive the formula, the chemical formula of the compound. All right? So here is the example. So let's say that we had a compound that had sulfur and fluorine in it, and it was 21.95% sulfur, and it was 78.05% fluorine. So the idea here is that the empirical formula can be determined from the percent composition. All right, so here is how we would do that. And I'm just going to launch right into, well, let me think here.
Okay.
Yeah, okay, so before I start doing the calculation, there's a couple more things we want to put in our notes. So the key is this right here. You assume that you have 100 grams of this compound. And so what that means is that if you have 100 grams of the compound, then 21.95 of those 100 grams is due to the sulfur, and 78.05 of those grams are due to the fluorine atoms, right? So that's the idea. So 21.95% of 100 grams means you have 21.95 grams of sulfur because of that percentage. Same thing for the fluorine. 78.05% means that you have 78.05 grams of fluorine. Okay, so that's kind of step one. You just convert the percentages into grams. So 21.95%, convert that into 21.95 grams. Okay, so the next thing we're going to do is we are going to convert the number of grams into number of moles. Okay, so this is where I will do it, and then it'll show up in PowerPoint. Okay, all right, so we have 21.95 grams of sulfur, okay? And I want to convert that into moles. So remember how we did this yesterday. 1 mole of sulfur is, what is the molar mass of sulfur? Well, it's the same thing as the average atomic mass of sulfur, but just with units of grams per mole. So that's 32.066 grams of sulfur. Okay, that's from the periodic table. So grams of sulfur cancel, and you get units of moles of sulfur. Okay, so some number of moles of sulfur. And then I do the same thing with the fluorine. So I got 78.05 grams of fluorine. And the molar mass, according to the periodic table, says that 1 mole of fluorine is 18.998 grams of fluorine. So grams of fluorine over grams of fluorine cancel. So I get some number of moles of the element fluorine. Okay? All right, so I'll erase that and show it to you, the PowerPoint. Okay, the number turns out to be 0.6845 moles of sulfur and 4.108 moles of fluorine. Okay, so that's the next step. We changed the percentages into grams, and then the second step, we converted those grams into moles, just like we learned about yesterday. Okay, so we could put these as the subscript. So for example, let me go back to showing you something here. So the formula you could legitimately write as this. This compound has sulfur in it and fluorine in it. So I could put as a subscript 0.6845, and as a subscript on the fluorine 4.108, okay? But we typically don't like to put subscripts that aren't nice, whole, integer type numbers. So now we're going to talk about how to fix this, how to make it prettier, basically, right? Okay, so erase that, advance the slide. Okay, so the way we do that, the way we get those nice whole number mole ratios is we divide each of them by the smallest number. Okay, so now get the mole ratios by dividing each number of moles by the smallest number.
Ah.
So I had 0.6845 moles of sulfur, so that is the smallest number, right? When you compare 0.6845 to 4.108, 0.6845 is small. So that's what I mean by divide each number of moles by the smallest number. So I divide that by itself, which means you get a nice whole number equal to 1. And then if you divide the 4.108 moles of fluorine by 0.6845, then you get 6. So you see that that comes out to be about 6. Okay, and a lot of times it will be something not exactly a nice whole integer, but that's when you got to round. If it's real close, you just round up or round down to the nearest integer. If it's something like a 0.5, then you multiply both of them by 2. If it's something like 0.25, then you multiply both of them by 4. So sometimes you have to do a little bit more math, but this is just the simplest example to get us started. Okay, so the mole ratios are the subscripts in the empirical formula. So what I just calculated here and here are the subscripts that I put into the empirical formula.
Woo!
Okay, so and remember a subscript of 1 is implied. I don't have to write it explicitly. Okay, so there's 6 sulfurs. Okay, so that's how you go from percent composition to the empirical formula. All right? All right, so now what I'd like for you guys to do is to work in small groups to do one of these where you have a compound that we know is 42.9% carbon and 57.1% oxygen. So I'm going to break you up into small groups. Let's see, I got 8 people. I think I'll just do two small groups again. And so I'll open all the rooms. All right, so feel free to join the groups and I'll pop in shortly. Okay, looks like everybody's back in the main session and I saw some good work in there. So we'll just quickly go through the solution to this. So first of all, we just again assume that we have 100 grams of it so that the percentages become a number of grams. Then you just convert each one of those into a number of moles. And so you get 3.57 moles of carbon, 3.57 moles of oxygen. So you divide each of those by the smallest number. In this case, they're both the same. So you divide them by 3.57, you get a 1, you get a 1. And so the empirical formula is just CO, or carbon monoxide. Okay, so hopefully that's what everybody got. Again, just a simple one to give you a little bit of practice with this type of problem. Okay, so now stoichiometry. This is one of those big fancy chemistry words. We like those. What it is, it's just a way to relate the mass of one thing in a chemical reaction to the mass of another thing in a chemical reaction. It could be another reactant, or it could be one of the products, but it's just a way to relate the relative masses of the things involved in the chemical reaction. Okay? All right, so here's the deal. This is what I use to teach stoichiometry. I call it the stoichiometry roadmap. And the big deal with stoichiometry is you cannot go directly from grams of a reactant to grams of a product or the other direction. Okay, you can't go from grams to grams. You have to go through moles. So it's like there's a roadblock there. Okay, so that's why I call it a roadmap. It's one way to think about it. I can't go directly from grams of A to grams of B. There's a roadblock there. So I got to take a detour. And the detour is through moles. So if I know grams of A that I have as a reactant and I want to calculate the grams of B that I will get as a product, then what I need to do first is I need to convert grams of A into moles of A, and I know how to do that based on our lesson yesterday. I just convert grams to moles by dividing by the molar mass. And then what you do is you use a mole ratio that comes from the balanced chemical reaction, which we also learned in yesterday's lesson. So that one of the big reasons for learning how to balance those chemical reactions is so you can get this mole ratio, so that you can do stoichiometry, so that you can relate the moles of A in a reaction to the moles of B in the reaction. And then once you know the moles of B through that mole ratio, then you can just convert that into grams of B by, if you remember, just multiplying by the molar mass of B. Okay, so it's what we call the stoichiometry roadmap. Now, you won't have this diagram on quiz day or on the day of the final, but the idea is that you do enough of these practice problems, you kind of just memorize it. It becomes a mental picture. All right, so let me do an example for you. So let's say that we have this chemical reaction. We have lead nitrate react with 2 sodium chlorides to form lead chloride and 2 sodium nitrates. And so the question is, what mass in grams of sodium nitrate, and this is the molar mass, would be produced if 2.34 grams of lead nitrate, molar mass right there, reacted with an excess amount of sodium chloride. Now that term there, excess amount, comes into play later. But for now, just know that we're not going to run out of sodium chloride. I have 2.34 grams of one of the reactant, and there's no way I'm going to run out of the other reactant. Okay? So just kind of setting the stage with our little diagram here. What I know is I have 2.34 grams of lead nitrate. So I can't go directly from grams of lead nitrate to grams of sodium nitrate, okay? That road is blocked, so I got to take a detour. And the way I do it is I first of all convert grams of the lead nitrate into moles of lead nitrate by dividing by the molar mass. And then I use this balanced chemical reaction to get the mole ratio between the sodium nitrate and the lead nitrate. So, and that's from these balancing coefficients. So for every lead nitrate that I consume, I produce 2 sodium nitrates. So that ratio is 2 to 1 in this case. So that gives me the moles of sodium nitrate. And so then I can just convert that into grams of sodium nitrate by multiplying by the molar mass of sodium nitrate. Okay? So that's the question. I want to go from here to here. I can't go directly. No direct route. So I got to go the detour way. I go through all these calculations to get to my final answer. Okay? All right, so we're going to divide by the molar mass, which is 331.2. Well, doggy. All right, and then that mole ratio we see here from the balancing coefficients is going to be 2 to 1. Okay, so we're going to multiply by this conversion factor, which basically allows us to translate from talking about lead nitrate into talking about sodium nitrate. So 2 moles sodium nitrates are produced for every 1 mole of lead nitrate consumed.
Okay.
And then once I know the moles of sodium nitrate, I change that into grams of sodium nitrate by multiplying by the molar mass of sodium nitrate, which is 85 grams, okay? All right, so now let me just kind of put all that into one long calculation, and then we'll show it to you in PowerPoint. Okay, so like I said, I'm going to start with what I know that's not a conversion factor, which is the fact that I have 2.34. I'm just going to start over again. 2.34 grams of lead nitrate, PbNO3 sub 2. Okay, so the first thing I need to do is convert that into moles of lead nitrate. So 1 mole of lead nitrate. And I know it's a pain in the butt, but I really do recommend writing out the full unit so that you can see things cancel. And so from that molar mass, I can see what that mass is. So 1 mole of lead nitrate is 331.2 grams of lead nitrate. Okay. So right now, grams of lead nitrate over grams of lead nitrate cancel. So right now I'm in units of moles of lead nitrate. But I don't care about moles of lead nitrate. What the question is asking about is the mass of the sodium nitrate. So I need to stop talking about this and start talking about this. And so that's where the mole ratio comes into place. That's the actual stoichiometry of it. And so the reaction tells me that I produce 2 moles of sodium nitrate for every 1 mole of lead nitrate consumed. Okay, so now that means that my units of moles of lead nitrate cancel. Okay, so the question asks for a mass though. So now I need to convert from moles of sodium nitrate into grams of sodium nitrate, and I do that by using the molar mass of sodium nitrate. So it says that 1 mole of sodium nitrate is 85.0 grams of sodium nitrate. Okay, so moles of sodium nitrate cancel, and so I end up with units of grams of sodium nitrate. So you plug that into your calculator, and you get grams of sodium nitrate. Okay. All right, so we'll erase that. Oops. I'll show it to you in the PowerPoint. So you can see all of the units canceling, and you plug that into your calculator. 1.2 grams of sodium nitrate. Okay. All right. So hopefully that makes sense. Now, so what I'd like you to do is to work in small groups again, and to work on this particular problem. So we want to know how much carbon dioxide would be formed if you use up 10 grams of C5H12. Okay, so let me put you into, oops, I lost somebody. I'll put you back into breakout groups. So we'll just go through the solution real quick here. So here's how you do it. And it's pretty much what I saw when you guys were working on it. So I know the mass of the C5H12, I need to convert that into moles. And then I use the mole ratio from the chemical reaction, that 5-to-1 mole ratio, to stop talking about the C5H12 and to start talking about the carbon dioxide. And then I just convert that into grams of carbon dioxide with the molar mass of carbon dioxide to get 30.6 grams of CO2. Okay, so hopefully that is what you got for an answer, and that it makes sense. All right, all the units cancel. That's really what's most important. Okay, so what I'd like to do next is to go ahead and set you up with a Chem 101 activity, but in order to do that, I want to, there's first I want to demonstrate how to do it in the Chem 101, and then I'll cut you loose to work on one. So I'm going to stop this share, and I'm going to share a different screen with you. Oh, not yet. Okay, so this is the the 2 demo, and so I want to demonstrate how to do a stoichiometry problem in Chem 101 with this scaffolding like you've used before, but this is a little bit more challenging because you have to add some terms to it. So here's our question: how many moles of H2SO4 are required to completely react with 7.2 moles of aluminum according to the balanced chemical reaction? 2 aluminum plus 3 sulfuric acid react to form aluminum sulfate plus 3 hydrogen gas. Okay. So remember, with these chemistry calculations, you always start with a number that you have that's not a conversion factor. And in this particular problem, and in a lot of these Chem 101 problems, you're not going to start at the beginning of the stoichiometry roadmap. You're going to start in the middle. It just kind of simplifies it to, we don't, in some of these problems, you don't have to solve for moles from grams. You're already given the number of moles, and that's what we have here. So 7.2 moles of aluminum, okay? And so what I can do, and since we're asked for moles of H2SO4, what I can do is just go ahead and go straight to the mole ratio. So I know moles of aluminum and I know moles of H2SO4 from the coefficients from the balanced chemical reaction. It's just you got to put them in the right place. So according to that reaction, every time I use up 2 moles of aluminum, I produce 3 moles of I also use up 3 moles of H2SO4. Okay, so that's the thing about stoichiometry is you can relate, like for example, a reactant to a product, or in this case, you can relate one reactant to another reactant. So that's kind of the utility of it. And so then you put in the answer box here, and so you can see that the units cancel for moles of aluminum. So you're going to have moles of, you're figuring out the moles of H2SO4 that you need. And so then you just do the math and you get the right answer. So you plug all that in your calculator. So 7.2 times 3, divide that by 2, and you get the 10.8. Okay, so that's the number that we're going to use. And you view the feedback, and you got the correct answer. Okay. All right. So what I will do then is I will stop this share, and I'll open up the next one for you. Okay, so I think I'll just go ahead and move on. Looks good. All right, so if you remember from the pre-class activity, you had to determine how many grilled cheese sandwiches you could make based on a limited number of ingredients. You had a limited number of slices of bread, you had a limited number of slices of cheese. And so all of that activity was to introduce to you the concept of limiting reactant, which is also called sometimes limiting reagent. Reagent, reactant, they're synonyms. So you'll see it both ways in different, it depends on the textbook or the instructor. I typically will call it limiting reactant. So what is a limiting reactant? That's just the substance that's depleted first in a chemical reaction. So you're going to run out of something first. And in the case of the activity that you did, you know, in one situation you ran out of the bread first, in the other situation you ran out of the cheese first. So it just depends on, first of all, how much of each reactant you have, but it also depends on their proportions. Like, you know, you need 2 pieces of bread with every slice of cheese. So, you know, those proportions come into play as well in determining which thing is the limiting reactant.
Hooray!
Okay, and the big deal with the limiting reactant is it determines the amount of product that can be formed. In the case of the activity, the number of grilled cheese sandwiches. Okay, so it will determine what's known as the theoretical yield. Theoretically, how much product could you produce if you started with that amount of each reactant?
Ah, crap!
Okay, so the idea here is that if you run out of something, then you're going to have the other reactant left over, right? So there will be some of the other reactant left over, and therefore, you know, just doesn't get fully utilized unless you have the proportions exactly right, the amounts exactly right. Okay, so that's the concept of limiting reactant. So grilled cheese sandwiches is great, but this is chemistry, right? So let's apply it to chemistry. And so we have this chemical reaction where we have hydrogen and oxygen reacting to form water, okay? So according to this balanced chemical reaction, I'm going to use up 2 hydrogen molecules for every one oxygen molecule that I need to use up to produce 2 water molecules. So this is kind of like, you know, bread and cheese. So let's carry out one reaction cycle, right? So I'm going to take 2 of these hydrogen molecules and 1 of those oxygen molecules and react them. So there, let's say it's these. So I use up those 2 hydrogen molecules and that oxygen molecule, and then let's do it again. Okay, so now I used up those 2 hydrogens and that oxygen. Now I use up those 2 hydrogens and that oxygen, okay? So the question is, well, which one ran out first? Well, you know, I've used up all of my hydrogen on this side. There's no more hydrogen. I did the reaction 3 times, and I used up all my hydrogen. So the hydrogen ran out first. And unfortunately, I wasted those 3 oxygen molecules. I had oxygen left over, right? Okay, so you can see them over here.
Oakley dokley.
They ran out of hydrogen, and then they have the oxygen left over. So I produced, created those 2 water molecules. Those created those 2 water molecules, and those reactants created these 2 water molecules.
Oakley dokley.
And then I have these 3 oxygens left over. Okay. All right. So that's how you would do it with pictures. Okay. And then in a minute, we're going to learn how to do it without pictures. But I think I do have another, you know, in the interest of time, I don't think I'm going to do this as a small group activity because I don't want to take up too much time. This was originally going to be a small group activity, but I'll just do it as an example. So in this reaction vessel, which substance is the limiting reactant and how many product particles are present when the reaction is complete? Okay, and so here's our reaction. So it takes 2 A's and a B to create a C. So I'm going to use up, you know, 2 A's and a B, 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 okay? And so you can see that what I do is that creates a C, that creates a C, that creates a C, that creates a C, and that creates a C. So I can't make any more than 5 C's because once I've, you know, done these reactions, these 5 reactions, I don't have enough A left to do another reaction. I still have 1 A, but you can see it takes 2 A's, right? So I can't do another reaction. So I ran out of the A first. So in this case, the A is the limiting reactant. But that doesn't mean that I totally consumed the A's, because in this case, I need 2 A's. But after I do these 5 reactions, 1, 2, 3, 4, 5, I still have 1 molecule, if you will, of A left over, but that's not enough to carry out another reaction, because a reaction requires 2 A molecules. Okay, so this is just kind of a variation on the theme. All right. Okay, so I think I do have a Chem 101 activity for you, so I'll tab over and let you work on that. Okay, so a couple people got this one wrong, so I do actually want to show you how I would approach this one. Yeah, actually I have to do this one this way. Okay, so here's how I would approach this one. So it says you have 1 mole of xenon and 1 mole of fluorine. How many moles of xenon tetrafluoride can you create in the following chemical reaction? Okay, so and you'll see this in just a second. We're going to do some calculations, but let me just kind of set the stage. So let's say that I have 1 mole of xenon, okay? And from the balanced chemical reaction, we want to know how much of that product we can form. Well, it's a 1-to-1 ratio in the case of the xenon. So 1 mole of xenon will create 1 mole of xenon tetrafluoride, okay? Oops. So those moles cancel, so my answer will be in moles of xenon fluoride. So 1 times 1 divided by 1 is 1 mole of xenon tetrafluoride. So that may be why some of you were answering 1 mole, but let's do it in terms of the fluorine, the F2. Okay, so I have 1 mole of F2, and according to the balanced reaction, it takes 2 moles of F2 to make 1 mole of XeF4. Okay, so moles of F2 over moles of F2 cancel. Moles of xenon tetrafluoride. Okay, so that's 1 times 1 divided by 2, so that is 0.5 moles of xenon tetrafluoride. All right, so this is the smaller number. So that's the maximum amount of product that I can form. I will never get to 1 mole because I'll run out of the F2 first, the fluorine first, right? This is my limiting reactant. The fluorine is my limiting reactant, okay? And so that's really what we're going to get into. And so the correct answer is 0.5, okay? And so I'm going to show you another example of that very soon. All right, so I'll stop this share, and I'll start another share. I'll go back to this one. Okay. Okay, so what I just demonstrated was really what we're going to talk about and put in our notes right now. So how do you determine the limiting reactant without pictures, so in a calculation? So what we're going to do is we're going to do some stoichiometry. We're going to use stoichiometry to calculate the amount of product that would be produced if each reactant was completely used up, okay? And then the reactant that would produce the least amount of product is the limiting reactant. Okay, that's the key. So whichever calculation shows you the least amount of product, that identifies your limiting reactant, and that identifies your theoretical maximum yield of product. Okay, so for example, so here's my balanced reaction, SO3 plus H2O to give H2SO4. What is the limiting reactant when 20 grams of SO3 react with 10 grams of H2O? Okay, so once again, what I'm going to do is I'm going to use the amounts that I'm given to calculate the theoretical amount of product that would be produced. So let's start with the SO3. So I start with the 20.00 grams of SO3. And so again, using my roadmap, my stoichiometry roadmap, the first thing I want to do is convert that into moles. So 1 mole of SO3 is 80.0 grams of SO3. So grams of SO3 over grams of SO3 cancel. All right, so I need to calculate the amount of product that would produce. And so it's a 1-to-1 ratio. For every mole of that I consume, I produce 1 mole of that. So 1 mole of SO3 consumed produces 1 mole of H2SO4. So moles of SO3 over moles of SO3 cancel. And then I go ahead and I calculate it out in terms of mass. You don't necessarily have to do that, but there's value in that, and I'll explain that in a couple slides. So the molar mass is we're gonna utilize the molar mass in this next step to change it into grams. So 1 mole of H2SO4 is well, I gotta figure that out. I think it's 98. So let me just calculate that real quick, sorry. Oh, I could just add the 2 together. Yeah, 98. So the mole, I don't know why I don't have this on the screen, but it's 98. So 98.0 grams of H2SO4 is 1 mole of H2SO4. This is the molar mass of H2SO4. Okay. Okay. And again, you can just get that from the periodic table. So moles of H2SO4 over moles of H2SO4 cancel. Okay, and so that gives you a certain number of grams of H2SO4. Okay, and I'm going to go ahead and calculate that. So 20 times 98, divide that by 80. I get 24.3, nope, 24.5. Okay, so 24.5 grams of H2SO4. That's if I run out of SO3 first. But now let's figure out what I would get in terms of product if I run out of H2O first. So I do the same calculation with H2O. So I have 10 grams of H2O. And so once again, I convert that into moles. So 1 mole of H2O is 18 grams of H2O. Grams of H2O cancel. And it's still a 1-to-1 ratio according to the balanced chemical reaction, 1, 1. So 1 mole of H2SO4 for every 1 mole of H2O. So moles of H2O cancel. Okay, and then once again, I change that into grams, 98 grams of H2SO4 for every 1 mole of H2SO4. Moles of H2SO4 cancel. And so I have grams of H2SO4. Okay, so that will get me grams of H2SO4 based on the water as a reactant. Okay, so 10 times 98, divide that by 18. So that's, if I did the calculation correctly, 54.4. Okay, so 54.4 grams of H2SO4. So this is the smaller one. So it's the smaller. And so the key is this is, the SO3 then is my limiting reactant. And this is also the maximum amount, this is going to be the actual theoretical yield. There's no way I can get to 54.4 because I'm going to run out of my SO3 first. And so the maximum amount of product I can expect is 24.5 grams. Okay. All right. So let me just show you that in PowerPoint, make it look a lot prettier. Okay, so we're going to use stoichiometry to calculate how much H2SO4 is produced if each reactant is used up completely. So for the SO3, start with the 20 grams, convert that into moles.
Mole, 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 mole.
Figure out the number of moles. In this case, in this solution, apparently I didn't go all the way out to grams, but that's okay.
That's high quality H2O.
So for water, you do the same thing, and you get 0.555. So again, because this number is smaller.
Am I right or am I right or am I right? Right.
So that's the smaller amount of product. So the sulfur trioxide is the limiting reactant, and it will run out first. Okay, so that really answers the question. This question really just asks for which is the limiting reactant. But we went, and the solution that I did, freehand, showed you actually the theoretical yield as well. Okay, which is what I go through in this example. Okay, so in this example, we wanted to calculate a few more things. First of all, we want to determine what the limiting reactant is. Then I want to know how much water is going to be produced based on that, based on what reactant is limiting. And then I want to determine which reactant is left over. Okay, so very similar to what we just did in the previous example. Okay, so part A, what is the limiting reactant? Okay, well, once again, the way I figure this out is I just start with the amount of, each reactant that I have and figure out which one, using stoichiometry, figure out which one results in the least amount of product. Okay, so we'll start with the methane. So we have 10 grams of CH4. Okay, so the first thing I want to do is convert that into moles. And so 1 mole of CH4. And I'm just going to kind of do this mentally. Carbon is 12, each hydrogen is 1. So that's 4 plus 12 is 16. So that's 16 grams of CH4. So I'm just, simplifying in the interest of time. So grams of CH4 or grams of CH4 cancel. So 1 mole, this is the molar mass of CH4. And now I use the mole ratio from the balanced chemical reaction. So that's, 1 to, the product that I'm concerned with later is water. So I'm going to relate it to the water. So it's 1 to 2. So I get 2 moles of H2O for every 1 mole of CH4. Now you might be wondering, could you do it based on the amount of carbon dioxide produced? Yes, but because this specific question later in part B asks how much water is produced, I'm going to go ahead and relate it to the amount of water. Okay, so moles of CH4 over moles of CH4 cancel. All right, and then I just use the molar mass of water, 1 mole of H2O. Again, just simplifying things, is 18 grams of H2O. Okay, the molar mass of water is 18, so moles of water over moles of water. So I get grams of water, okay? So that's gonna give me a certain number of grams of H2O. So then I do the same calculation with the other reactant. So that's 20 grams of oxygen. So 20.0 grams of O2. And the first thing I do is convert that into moles. So 1 mole of O2. Now this is the error that a lot of people make. It's O2. So the molar mass of O2 is 32 grams. Okay, so a lot of students are tempted to put 16 here because oxygen has an atomic mass of 16. But the molecule is O2, and that's what I'm consuming. I'm consuming molecules of O2. So the molar mass is 32. So grams of O2 over grams of O2 cancel. And now I do the mole ratio just like I did here. So in this case, it's 2 to 2. So I get 2 moles of H2O for every 2 moles of O2 that I consume, 2 to 2. So moles of O2 over moles of O2. And so once again, I just change that into mass of H2O. Okay, so moles of H2O over moles of H2O. And it gives me a certain number of grams of H2O. Okay, so then you're just going to compare those, right? And I'll let PowerPoint get us to that point. But whichever one of those is smaller, okay, that's going to identify the limiting reactant. Okay, so I'll erase all that, and I'll show it to you in PowerPoint. Okay, so we're going to do it based on methane.
Mole, 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 mole.
Mole ratio, change it to mass of the product. Everything cancels for grams of water, which is what I'm looking for. I get 22.5 grams of water based on the methane, the CH4.
How you doing?
I do the same thing based on the oxygen. Okay, change it to moles, mole ratio, change it to mass of water. Everything cancels except for grams of water. I get 11.3 grams of water. So because that is the smaller number, okay, that means that oxygen is going to run out first. Oxygen runs out first. It's the limiting reactant. And the other thing that's nice is this identifies the theoretical yield. So the maximum amount of water we can expect is 11.3 grams. And so that's really the answer to the next question. Okay? Part B says, how many grams of water will be produced? Well, that's really what we just solved in the previous slide. I don't have to do any more work. And so that's part of the reason why I recommend that when you're doing these limiting reactant problems, that you go ahead and take it out to, the mass of the product, because that may be useful information for later in the question. Okay, so when you identify the limiting reactant in this way, you also calculate the answer to this part of the question, 11.3 grams of water. And that has a special name. We call that the theoretical yield. Okay, so we answered part A and part B. Okay, now the last part of the question is how much of each reactant is left over? Okay, well, one of them is real easy. It's kind of a no-brainer. One of them ran out, right? One of the reactants is limiting, so it runs out completely. And we decided that it was oxygen. So the oxygen is easy. None of it is left over because it ran out first. Okay, so now let's talk about the methane. So what I need to do in this case is, if you don't mind, I'm just going to go through this in PowerPoint in the interest of time because we are getting a little bit close to the end of class. So we have to figure out how much methane, we're going to use stoichiometry to figure out how much methane was consumed. So let's do that based on the amount of oxygen that was consumed, which is all of the oxygen.
I don't understand.
Okay, so that's why I start with the 20 grams of oxygen. So I got to figure out how much methane is consumed. So I know how much oxygen was consumed, and I'm going to use that to determine how much methane was consumed. So all of the oxygen, which was 20 grams, was used up. So how many moles of oxygen is that? Well, again, I use the molar mass of oxygen to figure that out. So 20 grams of oxygen times 1 mole of oxygen is 32 grams of oxygen. So grams of oxygen over grams of oxygen cancel. So now I have moles of oxygen. All right, so if you think about your stoichiometry roadmap, the next thing I'm going to do is I'm going to relate the moles of oxygen to the moles of methane based on the balanced chemical reaction. So it's a 2-to-1 ratio. So 1 mole of methane is consumed for every 2 moles of oxygen that get consumed. So moles of oxygen over moles of oxygen cancel. So right now, my units are moles of methane. So I just need to convert that into mass of methane so that I can subtract it from the original 10 grams. So the next step is I'm going to multiply this times the molar mass of methane, which is 16. Moles of methane over moles of methane will cancel, and I will end up with a number of grams of methane. Okay, so if you punch that into your calculator, you get units cancel.
Well, Lottie frickin' God!
So you get 5 grams of methane have reacted. Well, I originally had 10 grams of methane. So 10 minus 5 is 5. So I have 5 grams of methane left over. So I used up all of my oxygen. I got no oxygen left over. But I didn't use up all of my methane because I ran out of oxygen before I could consume all of my methane. And so I did some stoichiometry to figure out how much methane was consumed, 5 grams of it, and I subtracted that from the original amount of methane and determined that I ended up with 5 grams of methane left over. Okay? All right, so that was a challenging problem. Multi-part, a lot of stoichiometry. So if you need to look at the video later to go over that again, no problem. And you'll get more practice with this, with the homework and the extra practice problems. Okay, so again, I was gonna have you do these in small groups, but in the interest of time, I'm just gonna go through it as an example. So let's say that I have this chemical reaction, these are the molar masses, and I have 100 grams of each, these two reactants. I got 100 grams of PCl3, I got 100 grams of Cl2, and I wanna know how much the product is gonna be formed. And also in the process, I'm going to determine which one is the limiting reactant. Okay, so I start with 100 grams of PCl3. So the first thing I need to do is convert that into moles. The molar mass of PCl3 is 137.3. So I convert that into moles of PCl3. And then I see that it's a 1-to-1 ratio. For every mole of this I consume, I produce 1 mole of this. So I do the 1-to-1 ratio. Okay, and then I need to convert that. So now if you look at the units, moles of PCl3 over moles of PCl3 cancel. So now I'm in moles of PCl5. So I want to convert that into mass of PCl5, and that's going to be done with the molar mass of PCl5, 208.239. Okay, so mole of PCl5 over moles of PCl5, so I get grams of PCl5, gives you 151. All right, so that's how much PCl5 I would get if PCl3 runs out, if I use up all of that PCl3. Let's do the same calculation with the Cl2, the chlorine. Okay, so 100 grams of chlorine. Now, this is going to result in a different number of moles of chlorine because it has a different molar mass, 70.906. So convert that into moles with the molar mass. So grams of Cl2 over grams of Cl2. I have moles of Cl2. It's still a 1-to-1 ratio. One of these produces one of these, 1-to-1. So now moles of Cl2 over moles of Cl2 cancel. So right now I have moles of PCl5. So then I just do the same last step as I did above, right? Just convert moles of PCl5 into grams of PCl5 using the molar mass. So you do that math, plug all that into your calculator, you get 293.816 grams. So that is a larger number.
Kind of makes you cry, doesn't it?
So since this is the smaller amount of product, that means that the PCl3 is my limiting reactant. I'm going to run out of it first, and the 151 is my theoretical yield. Okay, I can't get any more PCl5 than this. So I'm going to use up all PCl3. I'm going to have some Cl2 left over, and at most, I can produce 151.699 grams of PCl5. All right, so that's how you do that one. Hopefully it's making sense at this point. And would recommend that you do these that I went through rather quickly. It would be good for you guys to try on your own later on. Okay. All right, so we have a Chem 101 activity, but we just don't really have time for it. I'll open it up after class today for you to work on. It is a limiting reaction problem. And so we'll stop there. And so before tomorrow, you want to do your pre-class assignment, and the homework questions that are applicable to what we talked about today are 6 through 10. And then some more recommended extra practice problems and some good tutorial videos if you want, if what I said today maybe doesn't make a whole lot of sense, then here's a lot of good extra videos that you can watch that maybe help you understand it as well. Okay. All right. Thanks everybody for hanging in there. I know that was kind of a tedious lesson, and I appreciate it. So contact me outside of class if you have any questions or need anything from me. All right. Appreciate it. See you tomorrow.